Greetings. You're probably here because of the title, Brag Bash Retrieval-Augmented Generation. My name's Jerry Nettrower, and I'm the founder of this 501c3 nonprofit organization. And I created this Bash RAG so that I wouldn't have to utilize all the Python dependencies. The source code for it's here. It's I think it comes in under 25K, right? So it's not right. Like if you look at it here, it's not a lot. So I do have a GitHub repository for it. GitHub, if you want to get it from GitHub. I'll go ahead and copy this URL for my GitHub, and then I'll come in here and do a git clone, paste it, and put a .git, so I can get the source, then cd into Brag, and here it is. I have chunks.c cosine cu, which is the CUDA core. Oh, let me backtrack a little bit. Here, I put the requirements. It's also in the README. If you look at the readme.txt, I also put it in here. But it requires a C compiler, the CUDA toolkit. I specifically used CUDA toolkit. I think it was 10.280 something. It's in the README file. Let me go into the directory, and I'll open up the readme.txt file, and I'll go through it here. I'll move this a little. So as you can see, I do have these files in it, and then I do go through this. I thought I described where I put the. I thought I described what CUDA toolkit I use. It's 10.2. something. I think it's like 89 or something. Anyway, that aside, to walk through this pipeline, if you want to go through it, so I can show you how to create this RAG using Bash and a few helper C programs, right? So a few C programs right there. The first thing I do is I compile this chunks.c into a just chunks. If my mouse keeps sticking, so if you see me do this every once in a while, it's because I'm fighting with my mouse. So we compile that. Okay. So we now have chunks as a program. And then in the README, I'll come in here, and we can create, from the README file, we can create a read chunks.txt with a -s. Well, here, I'll go ahead and go through each one of these files so we can take a look at them. So here's the chunks. And right now I have it set at 128 characters for chunking into, for when it chunks a file, it'll chunk it into 128, as near as possible to a 128 character string. So you can go through and read through the logic that I used. It doesn't do a perfect 120. It doesn't cut words off, but it'll go to the nearest end or beginning of a word. And then here's the cosine that uses the CUDA toolkit. Let me see if I can put highlighting on it for C. It's just C using the CUDA toolkit. See, CUDA runtime H. So, and its usage is cosine. Then you put the embedded file, which will be a JSON, an embedded file, then a query, right? And then when you look at the the query CUDA, you'll see it uses the embedded. Then when it runs this cosine program, I could either use the CPUs or the GPU, and I've got it set with the -N to use the GPU. So, and then I've got the embedded, right? The embedded SH, and you can set the module here, and then it runs the module. So for embedding this, and then what else do I want to? Okay. Anyway, try to make sure that like here's with this module loaded in for the embedding. Make sure that it matches the module for the embedding of your, right? So get query embedding, make sure it matches. Okay, if these are off, it could lead to some really crazy results. So just try to make sure they're the same. And then for your generation module, I'm also using Gwen 3 8B. Anyway, okay, so now that I got all that out of the way, the boring stuff, let's continue. So, okay, so now that I've got the chunks program made, I'll go ahead and run the chunks program on this very readme.txt file, and using the -S, it'll output it to the screen. Without the -S, it'll just carriage return, and you'll see another line, right? It'll just say J3600 brag and then carriage return. But with the -S, it's going to output that file while it's doing it. So there you go. And this should be around 128 characters on each line. So, and I think it's 35. I think it's 35 lines. And then from here, now that we've got our chunks, our readme.chunks.txt, so if we do an ls, you'll see we now have a readme, or not a readme, but it is the readme file, but it's a read chunks.txt. And that's what we're going to be embedding. We're going to be turning the read chunks into a readme Gwen embedding -8b JSON file. Oh, before I do this, I even put a note on here. I do have to have the Ollama serve up and running. So, just to make sure that the LLMs can use it. So, that's what I almost forgot that. Oops. So, here we go. I launched it. I do have an NVIDIA GPU, but it's not a very powerful one. This system is over a decade old. I launched this specifically so I could type in DMIDE code and show you the manufacturing date on this system, right? Although, even though it's old, it's the newest, most powerful computer that I have for doing AI work, okay? So you see, this system was manufactured on May 7th of 2013, which totally explains why it's taken me 460 hours worth of research and data processing and 60 hours worth of development to create this brag, because when you're working on a computer that's over a decade old, it takes a little while for it to do local, because I'm running Ollama's a local AI. So I'm running a local AI, and it takes a little while to run it because it's a rather old computer, and I suppose I could upgrade the video graphics card a little, but still, it's a pretty old system. I have upgraded it as much as I possibly can. This is the absolute, right? When I went and talked to an AI, what's the absolute fastest CPU I can put in this computer? It said E5-2687W. So I've got the fastest computer. I can only have 64 gigs of RAM, which come out to be 62 gigs of useful RAM, I guess. And then Yeah, so it's a computer that's over a decade old. So if you think this can't be run on old computers, well, it can't. Oh, there it is. I just spotted it. It's NVIDIA 10.2.89. So anyway, back to our regularly scheduled program. Okay, so from here, I'm going to start embedding. Yeah, this is going on too long. I gotta get through it. So now that we've got Olama up and running, and I've shown you that I've got a very weak computer doing this, I'm gonna run the embedding.sh. Oh, you know what? One more thing before I run that embedding, I gotta chmod these. I gotta chmod these bash scripts, or they're just gonna crash out on me. So, yeah. There we go. Now I don't have to worry about it. These are executable now. So now I can copy this embed.sh, read chunks to, and it's going to process. It's going to use Olama, the Gwen 3 embedding 8B to create a JSON file. So, and you here, I'll switch over to here just to show you. So here we go. This is the well, this isn't using the NVIDIA. It's actually, I believe, using the CPUs. How do I know? Because if we go over here and look at the system, the CPUs are starting to run, and they will run hot. Look at this. This one's at 90 degrees Celsius, 91 degrees. Like, this thing is really running. Wow, how did that thing run? I didn't think it'd run this hot. I think this is the hottest these CPUs have ever run. I've ever seen these CPUs run. This is crazy. Yeah, that fan needs to kick on and start running to cool these cool this CPU off. Hopefully it brings that temperature down. Wow. Look at that. Look how hot that CPU's getting. So yeah, it's really, if we go back and look, this is, it's each line, right? The 35 lines I have in this text file need to get embedded. So, and it does take a while for this to run, where in most computers, modern day computers, it doesn't take anywhere near this long, right? 27 seconds to generate the vectors for a single line, 34 seconds. And like I'm showing you, the heat on my CPU is getting into really dangerous territory. Okay, the fan's running now, and I can hear the fan really well. It's the computer's running the fan really hard right now, so it is cooling off a little bit. But yeah, it's really, this embedding's giving it a chore. So I'll go ahead and speed the video up so you don't have to wait through the entire embedding session. So I'll go ahead and let this run, and you can just watch. And once it goes back down to a normal rate like this, I'll know it's done. I'll know it's done embedding. But it'll also announce it here. There'll also be a line that says it's done embedding here. Okay. So here we have it. It finally finished. My system gets to take a break, right? All these CPUs get to cool down for a little bit because they were running some serious heat there for a while. So as you can see, it's tapering off now. My system gets to do a little bit more rest. But now that it's got this README Gwen embedding 8B JSON file, okay, so now that we've got this, we can use this to perform our generation, our query generations off of. And again, make sure I put a note in here. Oh, wait, before I move on, I do need to compile the cosine helper program. And again, this is just using the CUDA toolkit to help. It's using the GPU to help find the top K in the program. So I'm going to go ahead and compile that. All right, that'll just take a moment. Okay, and then you will see if I switch back here, you will see it hit the GPU just little by little. See how there's no hits to it? You'll see little bitty hits on the GPU because it doesn't take it long to do. It doesn't take it very long to do the cosine top K stuff. But as you can see, it took from that's 7, right? That's 7 o'clock, 7 p.m. It took from 1916-23 to 1933-16 for it to turn a text file, a simple text file like read chunks.txt, 35 lines, into a vector JSON file. And it did hit the system pretty hard while it was doing it. So next, now that we've got the cosine compiled, I'll go ahead and copy the query that we're going to use. I'm just asking it, who is the creator of the R.A.G pipeline from the CUDA-query.sh file. So I'll go ahead and execute that. And you'll see it doesn't show up very quick here. It often, you'll see the hit, you'll barely see it. It'll just be a little hit on it when it does it, if you even see it, right? I don't often see the hit, so, but you might. When it does the cosine thing, you'll see it. So, oh, they're 2%. Yeah, it's not a very heavy load. Anyway, when it hits it, it'll produce this. It'll match the query top K versus the file's top K and pull all the relevant lines. Right now, I have it set it at 10. I want it to pull 10 top K entries for the query. And then now it's going to hit Ollama again. Ollama's now going to be processing. You can see where our embedding left off. And now it's running through and it's going to hit the system again to compute, right? It's going to hit it again to compute who the creator of the R.A.G pipeline is. So let's see what it gets for an answer. Okay, so there you have it. After quite a bit of processing, the embedded JSON file and going through and handling the query for generation, it came up with the answer, Jerry B. Netrower II. So, and here's its thinking on how it found that answer. So we come in here and you can see where it says, greetings, I'm Jerry B. Netrower II, the creator of the R.A.G, the bash plus R.A.G pipeline project. So that's your demonstration of how you can use a few C programs and some bash scripts to create a complete Ollama LLM R.A.G pipeline, or R.A.G because it's bash. It's bash related. So that's it. That is a demonstration of my R.A.G, bash Retrieval-Augmented Generation. So I want to thank you for watching. And if you want to make any tax-deductible donations, you can do so right from my website. Thank you for watching.